Welcome to lecture number 18 of Signals and Systems. So I'm covering up the things that we just started in the previous class, that is regarding LTI systems. So we could learn about some of the interconnections, system interconnections and operations. Today we will be learning about the more about LTI systems and its properties. Okay, so let me share my screens. We are studying about chapter 2, time domain representation of LTI systems. Topics to be covered in this session are interconnections of LTI systems, relation between LTI system properties and impulse response. To summarize about the previous class, we could learn about the system interconnections and its operations performed, and we learned how to implement a system parallelly as well as cascaded, and we could learn the associative, commutative, and distributive property of the LTI system, the convolution. Okay, so today we will throw some more light on the same thing what we had started in the previous class. The objective of this section is to develop the relationship between impulse response and interconnection of the LTI systems. So here again we have two different kinds, parallel connections and cascade connections of LTI systems. To just recap the things that we have covered in the previous class, I have taken these slides. The parallel connection of LTI systems look in the same manner how I had shown in the previous class. Here we have two blocks. This is first one, this is second one. Both are equivalent. The proof we have observed it in the previous class itself. Here what happened is the input is fed to system H1 of t and H2 of t simultaneously, and the output of the first system is x of t convolved with H1 of t. The output of the second system is x of t convolved with H2 of t. When you sum it, that will result in y of t. Now, if I have a system wherein it's a sum of these two impulse responses H1 and H2, like H1 of t plus H2 of t togetherly, I call it as H of t. And if I feed the input x of t to this, output can be got by the convolution of x of t with h of t. So this and this y of t, if you compare, both will be resulting in the same answer. Hence, these two diagrams are equivalent. Okay, so this is called parallel connection of LTI systems. The same has been shown in the mathematical form. So y of t is equal to y1 of t plus y2 of t. y1 of t is x of t convolved with h1 of t, and y2 of t is x of t convolved with h2 of t. So this was one of the things that we studied in the previous class. And here there is a derivation or the proof for what we have done in the previous class. Same thing we had done y1 of t and y2 of t. These two things, equations I have written. Here it is a discrete time, hence I have to take the integration x of 2 h1 of t minus 2, that is here. y2 of t is integration x of 2 h2 of t minus 2 dt. So you know that integration of x of 2 is constant, so I'm taking it common. So what is left? H1 of t minus 2, h2 of t minus 2. Togetherly, I call it as h of t minus 2, which is in turn x of t convolved with h of t. So this is the distributive property that we have learned in the previous class. The impulse response of overall system represented by the two LTI systems connected in parallel is sum of their individual impulse responses. This is what is the learning out of this. Okay, so we can also represent it in this manner. Okay, we call it as distributive property of convolution. Applies for both CT as well as DT. This is the first thing that we studied. Next comes the cascaded connection of systems, wherein we have two systems connected back to back, H1 of t as well as H2 of t. So we call the output of the first system as Z of t, whereas input is X of t. And the second system impulse response is H2 of t, for which the input is considered as Z of t, which is the output of the previous system, and the output is Y of t. And to have the equivalent system of these two things when they are connected cascaded back to back is the convolution of these two systems which are connected and cascaded. It is equivalent to having H1 of t convolved with H2 of t. So here we have again a proof that we have done in the previous class. I have taken the diagram for your reference again here. The derivation goes like this. So y of t, look at the first block diagram. We are matching these two things. We are proving that these two are equivalent. So we are taking this y1 of t is z of t convolved with h2 of t. Z of t convolved with h2 of t. So z of t is the input, h2 of t is the impulse response. When I convolve it, I get the output. That is what is written here. In terms of mathematical model, if I want to write integration ranging from minus infinity to plus infinity, z in place of x I am having z tau h2 of t minus tau d2. Okay, so now z tau, what's the meaning of z tau? Z tau is the output of the impulse response h1 of t and input x of t. That is what we need to write. So when zt is x of t convolved with h1 of t, or z tau is x of tau convolved with h1 of tau. Now if I apply the formula of convolution, I get it as integration from minus infinity to plus infinity x of, in place of tau I am using v because tau is already used, x of v h1 of tau minus v, because it is in place of t I am having, in place of t I am having tau, hence I am using one more variable called v. Close the bracket, write the rest of the things. In place of z tau I have written this. This is z tau. So h2 of t minus 2. Now if I just open the square bracket, it is a double integration x of v h1 of so and so, h2 of so and so, dv d2. Now what we are doing is we are making operating a change of variable here. So change of variable can be worked as, I call this tau minus v as eta, tau minus t as beta. Now we will substitute it here. So we know that integration x of v is a constant. It's an input and it is specifically at something tau is equal to v. So this is a constant. So I'm taking it outside. So integration of minus infinity to plus infinity h1. So tau minus v, I represent it as eta. I'm writing it as eta. Then in place of tau, I write it as eta plus v. So eta plus v minus, if I take open the bracket, it will be minus v minus eta. This is what I get. Okay, so d eta and dv. So integration minus infinity to infinity x of v, I write it as it is. Now here you look into it. So this is nothing but so h1 of t h2 t minus v. This is also t minus v because t minus v is in the place of t now. So eta is like tau. So hence h1 t minus v, h2 t minus v. So integration minus infinity to infinity. So in general we call it as h of t minus v. So integration minus infinity to infinity x of v h of t minus v. So again v, it occupies the tau's place. So looking at it, I write the final expression x of t convolved with h of t. This is the same derivation that I had taken in the previous class. Okay. So with this, I can say that even it holds good the commutative property also, associative property also. Okay. So hence it has been proved that the system 1 and system 2 are, equivalent. System 1 and system 2 are equivalent. Now, I take the first problem of this section, very important one. I put a star mark here, very important. Equivalent system to 4 interconnected systems. There are 4 interconnected systems. This is being one, this is second one, this is third one, and this is fourth one. Okay, so respectively we call it as h1 of n, h2 of n, h3 of n, and h4 of n. X of n is the input, y of n is the output. And they have even mentioned what is the impulse response of the first system. H1 of n is given by u of n. H2 of n is given by u of n plus 2 minus u of n. H3 of n is given by delta of n minus 2. And H4 of n is given by a raised to n u of n. Okay, so this is an extra, I think I written it. Find the impulse response of the overall system. You need to write the overall system here. Means I should be having x of n, of course square bracket. There should be single system which is represented by h of n, and at the output you have y of n. So this h of n I need to find out, which we call it as overall system response or impulse response. So h1 of n, h2 of n are in parallel connections. When they are in parallel connection, how do we write it? I just take you to the previous slide. When I have h1 and h2 in parallel, how can I write it? I can write it as h1 of t plus h2 of t, right? So same thing I write it here. So this one I write it here as, h12 means combination of these two things. of n is given by h1 of n plus h2 of n. It is by parallel. So the system's connected in parallel. Now what I do is this h12 is a combination of these two things. I put a dotted mark here. This whole of the system, now it is replaced by h12 of n. So now h12 of n and h3 of n are connected back to back or cascaded. When two systems are cascaded, I'll take you to the here. When two systems are cascaded, this being h12 of t, this is h3 of t. When it is cascaded, I need to convolve. The operation performed is convolution. So h12 and h3 should be convolved. For the naming sake, I call it as h123 because I'm combining all the three systems. So h12 of n convolved with h3 of n. And you know that what is h12 of n? h12 of n is h1 of n and h2 of n. That we will consider it later. Now what is the next one? The whole of this system, I am calling it as h123 of n, and it has been connected in parallel with h4 of n. So hence the final system h1234 is h123 of n plus h4 of n. That's it. This is my overall system. The same thing has been written here. This is a solution. Just have a look. h1 of n is, sorry, here there is a minus. You just check here. There is a minus. So it is minus. You should be very careful here. Minus. So minus h4 of n is already there. Now I need to write h12 of n. h12 of n is given here. What is h12 of n? h12 of n convolved with h3 of n. h3 of n is already there. h12 of n means h1 of n plus h2 of n. This is h1 of n plus h2 of n. This is equivalent to whatever I have written here. Okay, now what we are supposed to do is we need to solve for the overall system by applying these particular given system responses, impulse responses. Now we go one by one. I write h12 of n first. I'll take it here. h12 of n is given by h1 of n plus h2 of n. So what is h1 of n? h1 of n is u of n. What is h2 of n? It is u of n plus 2 minus u of n. Let me write it. u of n plus u of n plus 2 minus u of n. Okay, so you can see that u of n is in plus here, it is in minus here. These two things cancels. So what is left is u of n plus 2 is left. That is your h12 of n. Okay, so next is we have h123 of n. h123 of n is h12 of n convolved with h3 of n. That is what we write. h123 of n is h12 of n convolved with h3 of n. Now we already know computed h12 of n. It is u of n plus 2 convolved with, what is h3 of n? h3 of n is given as delta of n minus 2. Delta of n minus 2. So I had explained you separately regarding what happens when we perform convolution sum with the impulse function or impulse delta function. So here if we operate on this with a convolution, we get it as whatever I am having, write it, because anything that is convolved with delta function will result in anything itself, that other thing itself. So but here we have some modifications in time, that is time shifting is happening. So what you are supposed to do, n plus 2, whatever I'm having here, that also you need to take care. Okay, so you get it as u of n. So this is your h123 of n. Okay, we could solve till h123 of n. Now the last one, I don't call it as h1234 of n, rather I call it as h of n. h of n is given by h123 of n minus h4 of n. h of n is given by H1, 2, 3 of n minus H4 of n. So H1, 2, 3 of n is just above. You can write it. H4 of n is given by a raised to n u of n. A raised to n u of n. Or else this is 1 minus a raised to n u of n. So this is the overall system response. That was the question asked. This is the second problem. H1 of t, H2 of t, H3 of t. So all these three things are connected in parallel. I am feeding the input here, x of t. Now from H1 of t, it is directly going to H4 of t. So initially I call it as parallel, but there is some modification. Until every diagram is complete, we cannot decide whether it is parallel or anything else. It is added. Here also it is plus. Here also it is plus. Okay, so now this H4 is again summed up with the addition whatever I have got. Here I am writing minus symbol. You should be very careful here. H5 of t is the last system. This is your y of t. So this is a system diagram given. Now we have to compute h of t, overall system, but we have not been given the impulse responses of each of this. These are just denotions. You need to just write the h of t. So to write h of t, so we have to go one by one. H1 and H4, these are cascaded. So I write it here. H14 of t is given by H1 of t convolved with H4 of t. This is H14. So once it is done, I have to compute this. These two are parallel. H23 of t is parallelly connected. So I have to write it as H2 of 3 plus H3 of t. Now how about H14 and H23? So if I write it here, it looks like this. H14 of t, H23 of t. If these two are systems like this, now these two are connected in this fashion. This is like x of t, and these two are connected to summation, and here it is minus, and then it is h5 of t, and this is y of t. This is how it is connected. So hence what I'm supposed to do now, h1 2 3 4 of t is given by addition of these two things, h14 of t plus h23 of t. Now final is x of t is here, x of t is here. You have h1 2 3 4 of t is here, whole of this cascaded with h5 of t. When it is cascaded, the final response is h1 2 3 4 of t convolved with h5 of t, because it is cascaded. It is cascade. This is the final response. Now we will write it here. H of t is equal to h5 of t is already decided. Okay, so now h1 2 3 4 means here it is h14 h23. I go on writing here. H14 I write it first here. H1 of t plus h4 of t. These two things means it is h14. H14 is already taken care. Now what is h23? I have to add it. Plus h23 means h23 is written here. So h14, I guess it is convolution. I write it as convolution. Here it is added. h2 of t plus h3 of t. This is also put it in a bracket. The whole together we call it as h1 2 3 4 of t. Now whole together we need to convolve it. So I put a flower brace, convolved with h5 of t. This is your overall system response h of t. This is minus. In previous problem also it was there. Here also, you should be very careful. It is minus. So H14 is added. Here it is minus sign. You should have a minus sign here. H2 of T. H23 of T. So same thing here. It changes to minus. Okay, that's correct. Okay, please note this changes that I have made. So you should be very careful about the signs that has been mentioned in front of the summations. Okay, fine. So we'll move on to the assignment now. So H1 of n is given by 1 by 2 raised to n u of n plus 2. H2 of n is given by delta of n. H3 of n is given by u of n minus 1. Now the system is given as x of n, h1 of n. Now from here, h2 of n is connected in parallel to h3 of n. So these two are added, summation of these things. Here again minus symbol, I am highlighting it so that you should not commit mistakes here. This is y of n. Okay, so what you need to find is, first you need to find h of n question mark, and then substitute all the given responses and find out h of n at the end. Okay, so this is your assignment. So with this we will move on to the next one, that is relation between LTI system properties and impulse response. So I can call this as the last topic of the system properties. Okay, so first is a memoryless system, causal system, stable system, invertible system. You might recall that we had around 6 properties of the systems. We could cover only memoryless, causal, stable and invertible. The other two were linear system, and the one more is time invariant system. Why we are not taking in this following topics is because we are taking this chapter heading as LTI system. What is LTI system? It is linear time invariant system. Whatever we are considering is in this chapter are linear time invariant system. If I give any question, it is already linear time invariant system. So when it is already linear and time invariant system, so no need to check linearity as well as time invariance again. You need to check the remaining properties. Those are memoryless, causal, stable and invertible. So we will take one by one. This is memoryless LTI system. Continuous time as well as discrete time, both things I have taken here on the slide. To just have a recap, the output of the memoryless system depends only on the present input. Okay, so it should neither dependent on past or nor future. It only depends on present input. So if I just write the system, we write the system as relation between output as well as input, that is y of t and x of t, both are there, and h of t is also the representation of the system. So for h of t to be memoryless, it should not be dependent on either past or future value. So how to write it? Here is a way to write it. H of t should be 0 for any value that is t not equal to 0. T less than equal to t less than 0 or t greater than 0 means you will be having h like minus 1, h of plus 1. So like that you will be having certain values. So h of t is 0 for all these things. So it will be present only at origin. Okay, so h of t is dependent only at origin. So how to write it in the other way? This way is one of the way to write. The alternate way to write it is h of t is equal to some constant, but it is present only at t is equal to 0. How to write it? Multiply it with a delta function, because delta function is present only at t is equal to 0. So hence, when you multiply anything, a constant with a delta function, so it is mandatory that that constant exists only at t is equal to 0. Okay, so to check the memoryless component of the LTI system, you need to have h of t is equal to c into delta of t fashion itself. Any constant multiplied with a delta function is the only memoryless LTI system. Remember that. Or else this one. Both mean same. In discrete domain, integration is replaced by summation, and t is been replaced by n. Tau is been replaced by k. H of k is equal to 0 for k not equal to 0, or h of k is equal to c multiplied by delta of k. The same manner. This is how the memoryless system is decided. Now the next comes is causal LTI system. Causal LTI system's output depends only on the past input or present input. Past or present input. It doesn't depend on future value. That's it. Okay. So the convolution formula is here. So how to write it in this manner? H of t is equal to 0 for t less than 0. For negative axis means I had said you, if this is a t axis, this is the future values yet to appear. This is past value already appeared. This is at origin is a present. So anything which is dependent on past input or present input is a causal system. So for future value, if a future value is present, if output is dependent on a future value, it is not a causal system. Hence, what I do is h of t should be 0 for all the future value. That is how I'm writing here. Okay. So hence, what I do is normally convolution integral is taken from minus infinity to plus infinity. Here, what we have done is we are taking the integration of tau from 0 to infinity. Why we are not taking at minus infinity? Because it's a causal system. Causal system depends only on the past values or present values. Future value should be discarded. Hence, to discard it, minus infinity to 0, I'm not considering it. From 0 to infinity, I'm considering it. This is a causal system. Okay. Similarly, with the discrete time, you can see here y of n summation k ranging from 0 to infinity, not minus infinity to infinity. Minus infinity to 0 is discarded because it is a causal system. For causal system, it should be discarded. Okay. So this is how the system written. We'll be having a lot of problem solving with these concepts, so you should remember it properly. Now coming to the stable system. So bounded input, bounded output, stable system. Absolute summability of the impulse response. So in discrete time, your system response should be absolute summable. So when you take sum of k ranging from minus infinity to plus infinity, when you take the sum of all these impulse responses, it should be within the range, or it should be less than infinity. Then only we call it as bounded input and bounded output stable system. How to prove it? Y of n, h of n convolved with x of n, summation h of k, x of n minus k, summation h of k separately you take, x of x n minus k separately you take. For bounded input, considering that this is bounded input, it will result in a bounded output y of n only if this component is less than infinity. How to denote it? Here it is denoted. Okay, so it is denoted as here, summation ranging from minus infinity to plus infinity, mod of h of k should result in less than infinity. If this results in less than infinity, when you multiply it with the input which is bounded, it will definitely result in bounded output. So this is a condition. Remember, for discrete time. For continuous time, the condition is here. So absolute summable condition is here. Means the area under the curve of the impulse response should be finite. Area of the curve should not be infinity. It should be finite. Okay. So we can also call this as absolute summable. Okay. If it is having a finite area. This is how we decide the stability. So comparatively, stability of a system understanding seems to be a bit difficult, but if you practice one or two numerical examples, it will be again easy for you. Okay. So next, invertible systems. Invertible systems, convolutions, inversion, we call it as deconvolution. Okay, deconvolution is a process of recovering x of t from convolution that has been happened, h of t convolved with x of t. Okay, for example, x of t is convolved with h of t. X of t is convolved with h of t to result y of t. And if I feed this as an input to the second system, it will result in y of t convolved with h inverse of t, it will result back x of t. Then these two systems are called as invertible systems. So x of t convolved with, so here what I'm doing is these two systems are appearing cascaded. So when two systems are cascaded, so we have to convolve it. H of t convolved with its inverse, it will result in x of t only when these two systems are invertible. Only when these two systems are invertible, or else this way. H of t convolved with h inverse of t will result in delta of t, identity. H of n convolved with h inverse of n will result in delta of n. Sometimes it will be given like this. H of, so here in frequency domain you will get it. So let me not take it. H convolved with h inverse, capital letters. If it is written, you should write it as identity. So we will talk more about it in the next chapter, frequency domain chapter. Okay, so an exact inverse system may be difficult to find or implement. Determination of an approximate solution is often sufficient. So whenever you go try for invertible systems, it is not easy. For example, whatever I'm speaking, you're hearing through a medium called Google Meet. There'll be a lot of processing happening between the voice I'm speaking, and the things what you're listening. What you're listening at your end, it is a reconstructed signal. It is not an original signal. The original voice signal has been converted to the discrete domain and it has been transmitted to your end, and you are able to listen at the reconstructed signal. The reconstructed signal is so accurate that you can identify that it's me itself. But it is not actually 100% similar to my voice. It is almost similar. Okay, so that is what is a meaning called approximate solution. You are hearing an approximate voice of mine. Okay, so you can generate an approximate solution at the receiving, at I can say invertible end, and that is sufficient. Next, with this we will solve some numerical examples and then we will proceed with the further things. Okay, so we could learn about memoryless, causal system, stability and invertibility. Now we go take the first problem. For each of the following impulse response, for each of the following impulse response means denoted by h of t or h of n depending on discrete time or continuous time. Determine whether the given system is following things. First being memoryless, second being causal, third being stable. So right now we will not take invertible because invertible is a special kind of things. Most of the systems will not be invertible. Hence invertible topic I'll take it separately for numerical example solving. The very first example for your understanding is h of t is given by u of t plus 1 minus u of t minus 1. So this is the problem given. Now what you are supposed to do is, you know that u of t plus 1 is given by u of t plus 1 is left shift, one time left shift. U of t minus 1 is given by right shift. This is amplitude 1. Okay, so when you subtract u of t minus 1 with u of t plus 1, so if you subtract it here from minus 1 till 1, so it is not present. From 1 onwards, it goes on subtracting. Hence, h of t will result in a rectangular pulse ranging between -1 to +1 with amplitude 1. So this is a system given. Now you need to identify all these things. First one, whether it is a memoryless or memory, that we need to find. So it is not memoryless. It is not memoryless, or it can be said it is memory. Fine. So rather I write it as not memoryless because they have asked it as memoryless or not. So hence I write it as not memoryless. Why? Because the system also has a value at which is dependent on the past or future value. It needs a memory to store it. Okay, and it is not an impulse. I already said whenever a system to be called as memoryless, compulsorily it should be in this form: constant multiplied by delta function. You don't have any delta function here. Okay, so constant multiplied by delta function, it exists only at delta function, hence it is not an impulse. It's not impulse function, hence it's not a memoryless component or system. Next, whether it is causal. So causal system definition, I'll show it. Causal system is h of t should be 0 for t less than 0. You check here. H of t should be 0 for t less than 0. What about t equal to -1? For t equal to -1, what is your answer? At t equal to -1, amplitude is 1. So this fails. This is not equal to, hence it's not a causal system. It's not a causal system because it also depends on the future value. H of -1 is a future value, and that is a finite. H of -1 is 1. Hence it is not a causal system because it depends on the future value. Because it depends on future value. Future value h of -1 is 1. Fine. Now we have to decide whether it is stable. For deciding stability, it's a continuous time. For continuous time, the condition is integration ranging from -infinity to infinity, mod of h of t dt should be less than infinity. Integration from -infinity to +infinity, mod of h of t dt. So this is equal to, so here it is ranging from only -1 to +1. H of t is amplitude is 1 dt, so it will result in t ranging from 1 to -1. So 1 minus of -1 is 1, which is 2, which is less than infinity. Hence the system is stable. We call it as stable system. So this is how you need to compute the memoryless, causal, or stable. We call it as BIBO stable. Very simple. Okay, I hope there are no doubts for you. We will take up the next example. I call it as B. H of t is given by u of t minus 2 into u of t minus 1. Now we are supposed to write the waveform. U of t is given by a step here, amplitude, and it continues. U of t minus 1 is given by one time shift onto the right. This is how it is given. Now I have to scale by -2 because it is -2 here. -2 into u of t minus 1. So what happens? So this at 1, amplitude is -2 and it continues thereafter. This is -2. So hence if I write h of t's waveform, this would look like, so from 0 to 1, you have amplitude 1. Okay, from 1 onwards this is getting subtracted by -2 amplitude. 1 minus 2 is -1. So thereafter it will continue. So this is the h of t. Now whether it is memoryless or not memoryless, it is dependent on the past values, hence it is not memoryless. For memoryless, keep one thing in your mind, it should be in the fashion c into delta of t. It is not in that fashion, so it is memoryless. Now second one, whether it is causal system, Do you find any future values? You don't find any future values because h of t is equal to 0 for t less than 0. It is true. Hence it is causal system. Now, third one. What about its stability? You can check that your system function is growing till infinity. When it is growing till infinity, you have to apply the integration till infinity. The area under this curve, and this curve does not does not end it itself. When curve does not end, its area will be infinity. Hence, it is not BIBO, not BIBO stable, or else you can call it as unstable system. Unstable system. Just remember one thing, if any curve h of t is growing till infinity, then come to the conclusion that it is having an infinite area under the curve. Area under the curve means integration ranging till 0 to infinity. Hence, it is unstable. Okay. Next, h of t is equal to e raised to minus 2t u of t minus 1. Is it memoryless or not memoryless? You can check here. E raised to minus 2t. E raised to minus 2t is the exponentially decaying function. Exponentially decaying function. You can write it in this manner. But it extends till infinity. It will reach 0 when t reaches infinity. Okay, this is e raised to minus 2t. U of t minus 1 means? U of t minus 1 means a step function. It is also going to infinity. It is also going to infinity. Only thing is here it will result in 0. But from here onwards, it will reach till infinity. Okay. So, but whether it is, first we will go one by one, whether it is memoryless or not. It is not memoryless. Very straightforward, because you don't have c into delta of t. It is not an impulse. Direct conclusion, not memoryless. Now, whether it is causal or not. Causal system's condition is h of t should be 0 for t less than or equal to 0. Is it valid here? You just check. You don't find any of the future values. You don't find any of the future values. Hence, it is true. Therefore, it is causal system. It is causal system. Now, what about stability? Stability is, condition is minus infinity to plus infinity, minus infinity to plus infinity, h of t d of t. Now here it is going till infinity. It is also going till infinity, but it is getting multiplied. Means when I multiply it, it somewhat looks in this fashion. So it will reach. From here it is 0, because 0 into anything is 0. So it will go in this fashion till infinity. So what kind of a signal it is? It is diverging or converging? It is a converging type. All converging signals are of stable system. For stability, the system or the graph or the signal should be converging, and it is converging. Hence, it can be proved to be stable. So let me prove it to be stable. This is equal to from 1 to, this is from 1, because at 0 it is 0, from 1 to infinity, from 1 to infinity, h of t is given by e raised to minus 2t. Right? I have already taken care u of t minus 1 by writing limits 1 to infinity dt. This will result in e raised to minus 2t divided by minus 2. Once you have to put infinity, once you have to put 1. So this will give you e raised to minus 2, here infinity, this is minus 2, minus e raised to minus 2 divided by minus 2. Okay. So this will give you e raised to minus infinity means 1 divided by e raised to infinity. E raised to infinity is a very large number, I can say. It is a very large number, infinitely large. So when you divide something by very large number, you will get it as 0. You will get it as 0. Okay, 1 divided by 1 crore will give you a 0.000 something, so it will result in 0. So hence this will result in 0. Minus into minus becomes plus. It will result in half e raised to minus 2. If I use a calculator, I'll get the answer as 0.06, which is less than infinity. Hence it is a stable system. So normally people confuse here, thinking that it is extending till infinity. They will decide that it is an unstable system, but it is not true. As the system is converging, it can be stable. So you need to check it like this. Okay, this is a third example. Now the next example on the similar grounds, h of t is equal to e raised to minus 2 mod of t. This mod of t you should be very careful. So the graph, I'll write it. When t is positive, it is e raised to minus t. E raised to minus t already we had written in the previous example. It will look in this manner. This is e raised to minus 2t. So when I substitute negative values of t, minus of minus t is e raised to 2t. But it is only in negative direction. So negative direction, it is increasing exponential, which is e raised to 2t in the negative direction. For t less than 0, it is for t greater than 0. This is how it looks. Okay, it is at 0. Now we need to decide whether it is memoryless or not memoryless. So first to decide memoryless, you know that h of t is not equal to 0 for t not equal to 0. It should be equal actually, or c into delta of t. It is not in that manner. Hence it is not memoryless. It's best practice if you write everywhere like this. In previous problem also you could have written it as h of t is not equal to 0 for, in this manner, for t not equal to 0. It should be equal to 0 for t not equal to 0. Okay, so but it is not happening. Here also you should write it in the manner, same manner. H of t is not equal to 0 for t not equal to 0. So everywhere this condition is good if you write. For memoryless, what happens is h of t is equal to 0 for t not equal to 0. Okay. So next, causal system. H of t is equal to 0 for all t less than 0. That you need to check. Is it true here? For t less than 0, you have some value, finite value. Hence it is not equal to 0. So it is not causal or non-causal system. Third one, is it stable? Is it stable? That we need to check. For stability, the condition is minus infinity to minus plus infinity h of tau or t d tau. This can be written as, say, minus infinity till 0. It is varying in the fashion e raised to 2t dt, and for the 0 to infinity range, it is e raised to minus 2t dt. So you need to solve separately. If you solve separately, you will get it as e raised to 2t divided by 2, 0 to minus infinity, plus e raised to minus 2t. Let me write t itself, 2 you ignore, minus 2 ranges infinity to 0. So if I substitute, you will get it as e raised to 0 divided by 2 minus e raised to minus 2 infinity. 2 minus infinity is minus 2 infinity divided by 2 plus e raised to minus 2 infinity by minus 2. Here minus e raised to 0 divided by minus 2. So this is what you get. So here e raised to 0 is 1. So 1 by 2 minus e raised to minus infinity. I have already shown you that it is 0 plus this is 0 plus half. Half plus half is 1, which is less than infinity. Hence it is stable system. So you should be very careful when solving e raised to infinity is big number, large number. E raised to minus infinity is as good as 1 divided by e raised to infinity. It is 1 divided by large number, which is very small number or 0. Let me stop here. Thank you then.